Aloha, everybody. This is Gigi from Kauai Community College. In this video, I will be talking about volume by shells, and this is a second video in the series. So watch the first one that give you the general idea first, okay? So this one, I'm gonna compare the shell and the washer and when you would choose what. All right, so suppose you have a region of y equals x to the third, y equal to 0, x equal to 1, and x equal to 2. The region bounded by those graphs there. Okay, now that looks like that. Okay, x equal to 1, x equal to 2, and y to the third, and then y to the 0 down here. We are going to rotate that about the y-axis. So rotate that about the y-axis. So I'm gonna go ahead and copy down the other side, give it a little three-dimensional effect. That's the shape that we want to find the volume of. Okay, not the interior there, but the color part right there on the outside of this solid. Now, so by shells, right? So let's think about one rectangular slice there in that region. And then we're gonna rotate this to get a cylinder looking shell, right? In order to find the volume of that one shell, we need the radius. So the radius right there is the x value. The height of this particular shell is going to be the function value, which is x to the third, okay? And then the thickness would be delta x. But we're gonna take a look at that one cylinder thing, slice it open, and that would be a three-dimensional rectangular prism like this, right? Where the height, again, is x to the third. The length right here is going to be the circumference of the circle. So 2 pi r, with r being the x value there. And then how thick? That would be delta x. So the volume of one particular shell is this particular blue shell right here is 2 pi x times x to the third delta x, which is x times x to the third is x to the fourth, right? Now, we are going to go ahead and set up the volume of the solid. So we will say the integral, and we would go from 1 to 2, because that's our boundary. 2 pi x to the fourth dx, that would be the area of the surface there, multiplied by how thick, that's dx, okay? And then we are going to go ahead and take the integral of that. Okay, it becomes 2 pi x to the fifth divided by 5, evaluate it from 1 to 2, plug in 2, plug in 1. That would be your f of b minus f of a when you have definite integral, right? And that should give you 62 pi over 5. Nice, right? As far as calculus go, there's only 3 steps. But we really need to understand where that comes from, and the picture really helps us here. All right, now what I'm gonna do next is I'm gonna say, well, you know, when we have seen this before, we have used slicing area solids like this, right? So why did we use shell? Could we have done slicing, volume by slicing instead? So go ahead and take a look at the same picture here. What happened if we are going to take a slice like this one? The thickness, right? So then the big R, the big radius is 2. The small radius right there is the X value. The thickness is gonna be delta y. We're having these horizontal slices here, right? Now the cross section would look like this donut shape here, and we call that some books will call that a washer, and this is going to be like a washer method, or we just say volume by slicing. So we need to go ahead and find the area of this shape, where again, the radius is the x value, and we know that y is equal to x to the third. So then x value is going to be cube root of y, and that's the small radius inside here. The big radius is going to be 2, because that's boundary on the outside right here. So then the area of that is pi big R square minus pi little r square, right? And then the volume of that solid is going to be the integral. We're going to go ahead and set up the integral, right? From where to where? Well, did you just see how that line just came up right there? Why did that line right here come up for me? Well, because when we are looking at these slices here, the slices moving along the y equals x to the third graph, right? Up until here, that only worked until here. And then the bottom part here, we have a big cylinder minus a small cylinder, which we don't need calculus to find the volume of. So we need to break the integral apart. So the first part would be the integral from 1 right here to 8. That's where the y value goes for y equals x to the third, right? From 1 to 8. And then the area of that cross section, the thickness dy in this case. And then we're going to say, well, I'm going to add on the big cylinder minus the small cylinder for the bottom here, where the height of the cylinder is 1, right? Take the integral. We have this right here, evaluated from 1 to 8. The area of the big cylinder would be the height of 1 and the radius of 2. So pi r square h minus volume of the small cylinder, pi r square h, where little r is 1 and the height is the same, which is 1. And then you can do that calculations on your own, but you would take a look at this and you would say, wow, that was a lot more work, right? So the shell method for this type of shape was much better. It was a lot nicer, right? So when you have a solid, when you're setting it up, always decide, do I want to use slicing or do I want to find volume by shells? Okay, and that is that for me.